Hi everyone, my name is Dylan Carrera. I am a postdoc at Iowa State, and I'll be telling you about the formation of planetesimals inside dust rings. In honor of the theme of this week's conference, our story begins with H.L. Tau. One of the most interesting discoveries in recent years is that so many protoplanetary disks have these rings of dust around them. These rings, of course, are caused by pressure bumps. So particles drift in the direction of the pressure gradient. If you have a very large bump, it can locally reverse the direction of particle drift and create a particle trap. But I want to emphasize that a particle trap is not needed to create a local overdensity of particles. So here I sketch a much smaller bump that simply reduces the rate of particle drift, and that alone will create a particle over density. It's similar to cars on a highway. If you're on a highway and there's a traffic jam, in the traffic jam, the cars typically don't stop. There's instead a localized region where the car speeds are slow and an associated localized overdensity of cars. So what I want to do is I want to investigate whether these particle overdensities can trigger plant formation by the stream instability. Without getting into a lot of detail, the stream instability, or the SI, is a hydrodynamic process that concentrates particles into dense filaments. That's what we see in that movie right there. And the idea is that if those filaments become dense enough, if the density reaches the Roche density, then that can trigger planetesimal formation by gravitational collapse. But the thing that you need to know about the SI is that it is only effective if you have some pre-existing concentration of particles. That depends on the particle size. So here's the plan. We're going to try to use a pressure bump to concentrate particles and ideally bring it to the point where the particle density is high enough that the stream instability becomes an effective and efficient process. And then we will rely on DSI to additionally concentrate particles into those filaments to reach the Roche density, and then gravitational collapse can take over and take us all the way, the rest of the way, to planetesimals. So here's my experiment. I ran 3D hydrodynamic simulations on a very long shearing boat. So I have here a sketch of the size of my shearing boat compared to the typical ones that you usually see in simulations of the SI. And I need the bots to be this large because I want it to be large enough to completely contain a pressure bump similar to the ones that we see in ALMA. So I made a bot centered at 50U with a pressure bump similar to the ones in some of the outer rings from HL tau. The dust to gas ratio is a standard solar like 1%, and we're going to rely exclusively on the pressure bump to concentrate particles to trigger the SI. The other thing that I want to keep in mind is that if a pressure bump is too large, it might be unstable to the Rossby wave instability. So that creates a bit of an upper bound. Now, I couldn't find a very reliable source that would tell me definitively what kind of size bump I can get away with, but there's some excellent work from On et al. That I'm using as a guide that gives me at least an estimate of the bump size that would be stable against the Rossby wave instability. So this is the width of the bump that I chose. Again, it's based on some of the larger outer rings from each tau. And I'll basically throw 4 darts in this parameter space. Our fiducial run is one of the largest bumps that we can be confident are stable against the Rossby wave instability. I have a couple others. The largest one is the bump that has an actual particle trap, and a couple of other points in between just to test the entire parameter space. And here's the result. Long story short, it works. The experiment works. I want to draw your attention to the green curve. This corresponds to my fiducial run. This is an experiment with centimeter-sized particles, corresponds to Stokes number of about zero point 0.1. The amplitude of the pressure bump is 20%. And so this is the one that is large, but still definitely inside the region that is stable against the Rossby wave instability. Here I have the Ross density. I have plotted the maximum particle density as a function of time. And as you can see, the particle density goes way past the Ross density, well inside the gravitational collapse. And in the simulation, we definitely see planetesimals forming. What else? Simulations that have bigger pressure bumps, not surprisingly, also form planetesimals. The very small pressure bump kind of hovers around the region of the Ross density but never really gets high enough to truly trigger gravitational collapse. So this is the good news. The not so good news is that for smaller particles, when I lower the particle size to just 1 millimeter, um, there's you can see some filaments from the SI, but the density never gets anywhere near high enough to even approach the Roche density. This is something that we need to look into later, but based on what we have so far, it looks like it would be difficult for the smallest particles to form planetesimals by the extreme instability, but more work needs to be done. Let's just focus for now on the run that did succeed. So I want to show you a movie. So I'll play the movie, I'll let it loop a few times while I explain what's happening. On the top plot, I have the gas density, so you can see the location of the pressure bump. The second plot is the dust over density on some arbitrary scale, and you can see the filaments that are associated with extreme instability. These filaments mostly don't do anything interesting other than just be localized over density. But when they cross this particular region of the pressure bump, the filaments get denser and the instability becomes more effective, and that does trigger planetesimal formation. In the bottom two plots, you see you see a 2D view of the dust density, one looking down on the disk and the other one looking along the azimuthal direction. And in either case, you can see the actual planetesimals forming. So in the second to last plot, I have circled the planetesimals in those white circles. Um, so those correspond to regions that are many times larger than the Roche density and that are well inside the region of gravitational collapse. Here's a result for a simulation that has a Barcode trap. It's similar as you might expect. The planetesimals form larger, form earlier, the particle clumps are larger, and the and the particles concentrate a little bit earlier than the actual point of zero headwind. And that makes sense if you know how the SI works, because the stream stability actually needs some headwind for it to be effective. So in conclusion, I have conducted large shearing butt simulations with a realistic pressure bump inspired by the pressure bumps that we see in ALMA, and a realistic solar-like dust-to-gas ratio, and we have seen the simulations actually produce self-gravitating particle clumps by the stream instability. We've seen that for centimeter-sized particles at 50, on a bump at 50 U, a particle trap is not needed to form planetesimals, and we had no trouble getting planetesimals for a pressure bump that was definitely inside the Rossby wave stable region. For millimeter-sized particles, things look very difficult. Based on what we know so far, planetesimals may never form for a particle size that small, but more work needs to be done. That's what I'm working on now. So I'm currently working on high resolution simulations, longer time scales to really determine whether mimilo particles really can't form planetesimals or whether it was some numerical limitation of my existing simulations. Thank you all for listening, and I hope to talk to you later.